Hi guys, this is the EdExcel A-Level Maths Paper 3 covering the mechanics paper from the October 2020 series. Question number 1. A rough plane is inclined to the horizontal at an angle alpha where tan alpha is equal to 3/4. A brick P of mass m is placed on the plane. The coefficient of friction between P and the plane is mu. Brick P is in equilibrium and on the point of sliding down the plane. Brick P is modelled as a particle, and using the model we have to find, in terms of m and g, the magnitude of the normal reaction of the plane on the brick P. So to do this question, we would have to draw a diagram to help illustrate what's going on. And we've also been given this information here, where tan alpha is equal to 3/4. And with this, we can find out what sine alpha is and what cos alpha is. So if we have over here a right-angled triangle, tan of an angle, that's equal to the opposite over the adjacent. So the opposite over here, that's 3. The adjacent, that's 4, and therefore the hypotenuse through Pythagoras, that's 5. So therefore, we see over here, sine alpha, that's equal to the opposite over the hypotenuse, so we have 3/5. Cos alpha, that's equal to the adjacent over the hypotenuse, so we have 4/5. We've been given tan alpha to be 3/4. And we know our results are right, because sine over cos, that's tan. 3/5 over 4/5, that's 3/4. So we've got this brick resting on an inclined plane. We have over here our angle alpha, and at this point I think it would be a good idea to add on the relevant forces. So we have over here the reaction, as shown here. We've got the weight acting from the centre going down. So here we have mg, and we were also told in the question that the coefficient of friction between P and the plane is mu, and we also know that the brick is sliding down the plane. So the brick is going this way, and therefore friction goes this way. So here we have our friction force. And I also think it's helpful to split up this weight force into its components. So if we do that, we have over here the angle alpha. We have mg, which is essentially the hypotenuse. Here we would have mg cos alpha, and here, parallel to the plane, we would have mg sine alpha. So for part A of the question, if we go back to the question, we have to find the magnitude of the normal reaction of the plane on the brick P. In other words, we need to find out what R is. So we would have to resolve perpendicular to the plane. So resolving perpendicular to the plane, we have R equals mg cos alpha. And we know what cos alpha is. We said here cos alpha was equal to 4/5, and therefore r is equal to 4mg over 5. And now for part B of the question, we have to show that mu is equal to 3/4. Well, for us to find out what mu is, we need to first of all find this friction force and recognise that friction is equal to mu times by r. And the way we can find this friction force is by resolving parallel to the plane. So for part B, if we resolve parallel to the plane, we have over here F, which is equal to mg sine alpha, and we know what sine alpha is, that's 3/5. So here we have 3 mg over 5. And now recognizing that F is equal to mu r, we have F, which is 3 mg over 5. This is equal to mu multiplied by r. We said r over here was 4 mg over 5. And now solving for mu is quite straightforward. We recognise over here the mg's cancel on both sides, the 5's cancel on both sides, so we have 3 equals 4 mu. In other words, mu is equal to 3/4. Now for part C of the question, brick P is now removed from the plane and a much heavier brick Q is placed on the plane. The coefficient of friction between Q and the plane is also 3/4. We have to explain briefly why brick Q will remain at rest on the plane. Well, if we consider our free body diagram here, we didn't know what M was for brick P. We still don't know what M is for brick Q. But when we carry out the arithmetic, if we leave everything in terms of M, you'd notice the mg's cancel will still end up with the same value of mu. And of course, that makes sense, getting the same value of mu, because we were told that the coefficient of friction remains the same as 3/4. So, we can say that the forces acting on Q will still balance as the M terms will cancel out. And now for part D of the question, brick Q is now projected with speed 0.5 meters per second down a line of greatest slope of the plane. Brick Q is modelled as a particle. Using the model, we have to describe the motion of brick Q, giving a reason for your answer. Well, here we can assume that the velocity remains constant, and if we have constant speed, then we would have no acceleration, and if we consider F equals ma, we can therefore conclude we have no resultant force down the plane. So Q slides down the plane with constant speed 0.5 meters per second, and because we have constant speed, we can therefore conclude we have no acceleration, and if we have no acceleration, thinking about F equals ma, we can therefore conclude there's no resultant force down the plane. Question number 2. A particle P moves with acceleration 4I minus 5j meters per second squared. At time t equals 0, P is moving with velocity minus 2I plus 2j meters per second. And for part A, we have to find the velocity of p at time t equals 2 seconds. Now, let's write down what we know so far. We know the acceleration is equal to 4I minus 5j meters per second squared. We also know the initial velocity u, that's equal to minus 2I plus 2j meters per second. Now we have to find the velocity at p when t equals 2. And if we go to our formula book, the formula we can use is v equals u plus at. The reason being, we want to find the velocity, we know the initial velocity, we know the acceleration, we know the time. So, for part A of the question, using v equals u plus at, we have v, which is what we're finding. This is equal to u, which is minus 2I plus 2j, plus the acceleration, which is 4I minus 5j, times the time, which is 2. And from this, we can work out what the final velocity is. So, we have minus 2I plus 2j, and then here, 4 times by 2, that's plus 8I, minus 5 times by 2, that's minus 10j, collecting like terms with the I components, minus 2 plus 8, that's 6. So we have 6I, 2 minus 10, that's minus 8. So we have 6I minus 10j. So therefore, the velocity is 6I minus 8j meters per second after 2 seconds. Now, for part B of the question, at time t equals 0, p passes through the origin, and at time t equals t seconds, where t is greater than 0, the particle passes through a point A. The position vector of A is lambda I minus 4.5j meters relative to O, where lambda is a constant, and we have to find the value of t. Now, to do this part of the question, if we go to our formula book, we can use this formula over here. The reason being, we know the initial velocity, we know the position, we know the acceleration, and we know what t is, that's capital T. And if we use that, we can find out the value of lambda. So for part B, if we use r equals ut plus 1/2 at squared, we have over here r, which is lambda I minus 4.5 j. This is equal to u, which is minus 2I plus 2j, multiplied by the time. We know the time to be capital T, and then we add on 1/2 times by the acceleration, so 4I minus 5j, multiplied by t squared. Now, for this to be true, we can find out the value of t, which makes the j components true, and then substitute that into the I components to find out what lambda is. So, for the j component, we have over here minus 4.5. This is equal to 2t plus, well, here we have a half times by minus 5. So we have minus 5 over 2 t squared. So if we rearrange, we have 5 over 2t squared minus 2t minus 4.5 equals 0, from which we can find out the values of t. So if we solve using the calculator, we have 5 over 2 minus 2 and minus 4.5. So it turns out we get 1.8 and minus 1. So we have 1.8 and minus 1, and therefore we can conclude that the time is equal to 1.8 seconds. And the reason for this, t must be greater than 0. Okay. So when we come to find out the value of lambda, we substitute this t equals 1.8 into the I component. So if we think about the I component, we have over here lambda. This is equal to minus 2 times by t plus half times by 4, so that's 2t squared if we multiply by the t squared as well. So substituting t equals 1.8, when t is equal to 1.8, lambda, that's equal to minus 2 lots of 1.8 plus 2 lots of 1.8 squared. And if we work all of this out, so we have minus 2 lots of 1.8 plus 2 lots of 1.8 squared. So we have minus 2 times by 1.8 plus 2 times by 1.8 squared. Turns out we get 2.88. So therefore, lambda is equal to 2.88. Question number 3. For the first part, at time t seconds, where t is greater or equal to 0, a particle p moves so that its acceleration a meters per second is given by a equals 1 minus 4t in the I direction and 3 minus t squared in the j direction. And at the instant when t is equal to 0, the velocity of p is 36i meters per second. And we have to find the velocity of p when t is equal to 4. So to do this question, we would have to recognize over here the way we can relate acceleration and velocity is through integration. So the velocity is equal to the integral of the acceleration with respect to time. So we will be integrating the acceleration function 1 minus 4t in the I direction and 3 minus t squared in the j direction. So carrying out this integration, we see that the velocity is given by, well, if we just consider the I, we have t minus 2t squared, that's integrating 1 minus 4t. So this is in the I direction, and in the j direction, integrating 3 minus t squared, we end up with 3t minus 1/3 t cubed. And then of course we have a constant of integration c. And We were told that the velocity when t is equal to 0 is equal to 36i, and we can use this information to find out what c is. And once we find out what c is, we would have a particular solution for the velocity, and then we can find out what would happen when t is equal to 4. So when t is equal to 0, the velocity is equal to 36i. So using this, we have 36i is equal to, well, here we end up with 0i, here we end up with 0j, and then of course we have plus c. So therefore, c is equal to 36i, and we can therefore conclude the velocity that's given by t minus 2t squared plus 36, all in the I direction. So I've just gathered all the terms involving an I. And in the j direction, we have 3t minus 1/3 t cubed meters per second. And we want to find out what happens when t is equal to 4. So when t is equal to 4, the velocity, that will equal 4 minus 2 times by 4 squared plus 36 in the I direction, and in the j direction we have 3 times by 4 minus 1/3 times by 4 cubed meters per second. And therefore the velocity after 4 seconds, well, in the I direction we have 8, and working this out, 12 minus 64 over 3, that's minus 28 over 3. So the velocity after 4 seconds, that's 8i minus 28 over 3j meters per second. And now for part B of the question, we have to find the value of t at the instant when p is moving in a direction perpendicular to I. Well, if we're moving perpendicular to I, we can see from here that the I component will equal 0. Of course, if the I component is equal to 0, we can set this I component equal to 0. So, for part B, when I is equal to 0, we have t minus 2t squared plus 36 equals 0. So with this we can find out what t is. So if we use our calculator, we have minus 2t squared plus t plus 36. So we get t equals 4.5, and t is also equal to minus 4. So in conclusion, as t is greater than 0, we can see that the time is equal to 4.5 seconds, and of course that's because t is greater than 0. For the second part of the question, at time t seconds, where t is greater or equal to 0, a particle q moves so that its position vector r meters relative to a fixed origin O is given by t squared minus t in the I direction plus 3t in the j direction, and we have to find the value of t at the instant when the speed of q is 5 meters per second. Now, if we have a position vector r, we can differentiate this to find out what the velocity vector will be. So, if we do that, the velocity vector v, that's equal to the derivative of the position vector. So we would have to differentiate t squared minus t in the I direction and 3t j. So we can find out what the velocity is. So the velocity is equal to 2t minus 1 in the I direction and 3j. Now this is the velocity, and we were told that the speed is 5. So the speed, which is the magnitude of the velocity, that's equal to 5. So if we use this idea, what we would have over here then is 2t minus 1 all squared plus 3 squared square rooted. This is equal to 5. So if we square both sides, we have 2t minus 1 all squared. Now 3 squared, that's 9. And squaring the 5, we end up with 25. So we have 2t minus 1 all squared is equal to 16. 2t minus 1, that's equal to plus minus 4. 2t, that's equal to 1 plus minus 4. So therefore we end up with 2t values. T is equal to 2.5 and minus 1.5. And therefore the only t value which is acceptable, that's equal to 2.5 seconds. And that's because t is greater or equal to 0. Question number 4. A ladder AB, as shown here, has mass m and length 6a. The end A of the ladder is on a rough horizontal ground. The ladder rests against a fixed smooth horizontal rail at C. And the point C is at a vertical height of 4a above the ground. The vertical plane containing AB is perpendicular to the rail. The ladder is inclined to the horizontal at an angle alpha, where sine alpha is equal to 4/5, as shown in figure 1. The coefficient of friction between the ladder and the ground is mu. The ladder rests in equilibrium. The ladder is modelled as a uniform rod. Using the model for part A, we have to show that the magnitude of the force exerted on the ladder by the rail at C is 9 mg over 25. Now, the first thing to think about is, which way will the ladder move if it slips? Well, if it slips, the ladder will be over here somewhere. So, because the ladder has essentially moved this way, the friction force will be this way. So here we have our friction force. Okay, let's just get rid of these annotations. Now, also, we know that sine alpha is equal to 4/5. So from this we can find out the value of cos alpha and tan alpha. So over here we know that sine alpha is equal to 4/5. Sine alpha, of course, is equal to opposite over hypotenuse. So we have the opposite 4 over here, hypotenuse 5 over here, and through Pythagoras the adjacent is equal to 3. So we have over here sine alpha, that's equal to 4/5. Cos alpha, that's equal to adjacent over hypotenuse, so that's 3/5. Tan alpha, that's equal to opposite over adjacent, that's 4/3. Okay, so with that, what we want to do for part A is find out the value of the normal reaction here. So if we annotate, we have over here at the point C, we'll call this N, okay? And here from the ground, we have R over here, and I think I will write F down in a different colour. We have over here F. And we've got the length of AB, that's 6A. Now the length from A to C, we can also figure out. That length we can work out using trigonometry. So this length over here, well, here we've got 4A, which is the opposite to the angle. This is the hypotenuse. So therefore this length through trigonometry is 4A over sine alpha. And the midpoint over here of AB, that's going to be at 3A. So essentially over here we would have somewhere over here, we'll add it in grey, the weight of the plank acting down. So the weight of the plank, we'll do it in red actually, that weight is equal to mg. Okay, and the distance from A to this point over here, that's equal to half of the 6A, which is 3A. Okay, so why is that useful? Because if we know these various lengths, we can take moments about A to find out what n is. Now of course when we take moments, we need to have a distance and a force, and the distance must be perpendicular to the force. So if we resolve parallel taking moments about A, so let's just write this down for part A, taking moments about A, well, over here, if we split this mg into its components, we have over here mg cos alpha, and here we have mg sine alpha, of course assuming this angle here is alpha. So that's quite useful, because if we take moments about A, we have n times by the distance for A over sine alpha. So let's just write this down. We have n times by 4A over sine alpha, and this is equal to mg cos alpha times by 3A. Okay, so mg cos alpha times by 3A. And with this we can find out what n is, and of course these are equal to each other because we're in limiting equilibrium. So if we tidy things up a bit, the a's cancel on both sides, so we have 4n over sine alpha is 4/5, so we have 4n over 4/5. This is equal to 3mg multiplied by cos alpha, which is 3/5. So if we simplify all this, on the left side, 4 divided by 4/5, you'd find that to be 5. So here we have 5n, which is equal to 9mg over 5, and therefore n is equal to 9mg over 25. Now for part B of the question, hence or otherwise find the value of mu. Well, for us to find the value of mu, we would first of all need to find out what r is. The reason for that is we should know that f is equal to mu r. And if we find out what f is and what r is, we can use those to find out what mu is. And we can find out what f and r are by resolving horizontal to the ground and vertical to the ground. So for part B, if we resolve horizontally, let's just go back to our diagram. We have f over here, and this is equal to some component of n. So to find out what that component is, we would have to split this n up into its components. So assuming we have the angle alpha over here, you can see over here n is the hypotenuse, this length here is the opposite, so here we have n times by sine alpha, and here we have n times by cos alpha. So with that, if we resolve horizontally, I hope you can see we have f equals n sine alpha. We know what n is, we know what sine alpha is. So we have f equals n, which is 9mg over 25, multiplied by sine alpha, which is 4/5. So we can conclude over here, f is equal to 36 mg over 125. Okay, and now if we resolve vertically, if we go back to our diagram, we have r over here, and the vertical component of this normal to c is n cos alpha, and we've got the mg going down. Of course, they're in equilibrium, so we have r plus n cos alpha, this is equal to mg. So we have r plus n, which is 9mg over 25. Okay, so this is what n is, multiplied by cos alpha, which is 3/5, and this is equal to mg. So if we tidy all this up, well, over here 9 times by 3, that's 27. So we have r plus 27 mg over 125, which is equal to mg, and therefore r is equal to mg minus 27 mg over 125. Well, if I work this out, 1 minus 27 over 125, you'd find that to be 98 over 125. So r is equal to 98 mg over 125. And we know what f is, we know what r is, so in other words, we can find out what mu is. So we have f equals mu times by r. So if we use this, we have F, which is 36 mg over 125, and this is equal to mu times by r, so we have 98 mg multiplied by mu over 125. The mg's cancel, the 125's cancel, so we are left with 36 equals 98 mu. So therefore, mu, that's equal to 36 divided by 98, which is 18 over 49. So we have 18 over 49 for the value of mu. Question number 5. A small ball is projected with speed u meters per second from a point O at the top of a vertical cliff, and the point O is 25 meters above the point N, which is on horizontal ground. The ball is projected at an angle of 45 degrees above the horizontal, and the ball hits the ground at the point A, where AN is equal to 100 meters, as shown in figure 2. The motion of the ball is modelled as that of a particle moving freely under gravity, and using this initial model, we have to show that u is equal to 28. Well, we can resolve horizontally and vertically to find out what u is. And if we resolve horizontally and vertically, again we'd have to make use of this formula, S equals ut plus a half at squared. Okay, so part A, if we resolve horizontally, we have S equals ut plus 1/2 at squared, and of course with horizontal motion there is no gravity. So horizontally, the distance S, that would be 100 meters, and this is equal to u. Now the component of u horizontally, that's u cos 45. So we have 100 equals u cos 45 times by t, from which we can rearrange, well, cos 45, that's 2 over root 2, so we can conclude over here t is equal to 100 over u cos 45. Okay, so here we have 100 over u times by root 2 over 2, so we would end up with 200 over root 2 u. So that's what t is. And if we consider the vertical motion, if we resolve vertically, that is, you can hopefully see over here, again using S equals ut plus a half at squared, so let's just write this down, S equals ut plus 1/2 at squared. We have S, which is minus 25. The reason it's minus 25 is because if we take O as the origin, we're going below O 25 meters. So S is equal to minus 25, and this is equal to u, the vertical component, that's equal to u sine of 45 multiplied by t. Now here, 1/2 times by a, that will be minus 4.9 t squared. Obviously we take upwards as positive, so gravity acting downwards will be negative. And we already know what t is. So what we have over here then is minus 25 equals u sine 45, which is root 2 over 2 multiplied by t. Let's just write this as on a separate line. So here we've got u times by root 2 over 2 times by t, which is 200 over root 2 u minus 4.9 times by t squared. So we've got 4.9 lots of 200 over root 2 u squared. So if we tidy all of this up, what we'd have over here is, if we tidy all this up, we would have minus 25 equals 100, and here we get 98,000 over u squared. Okay, so minus 98,000 over u squared. Okay, so if we rearrange for u squared, that's equal to 784, and therefore we can see here u is equal to 28. Okay, and now for part B of the question, we have to find the greatest height of the ball above the horizontal ground NA. Well, here we would have to resolve vertically, and this time we would have to use the formula v squared equals u squared plus 2as. S over here will determine the height above O, and of course the greatest height occurs when the velocity is equal to 0. So for part B, if we resolve vertically, we have v squared equals u squared plus 2as. So if I attempt to draw the motion of what I'm talking about, we've got something looking like this. I'll draw this a bit neater actually. We've got something like this. This is our projectile motion, and here is where we'd have the greatest height, and here the velocity is equal to 0. Okay, and also with this, if we find out what this height over here is, from here to here, we'll call this height h. The greatest height will be 25 plus this h. So using everything we know so far, we have 0 squared. This is equal to, now we are resolving vertically here, so here we have 28, that's u, times by sine 45 squared minus 2gh. So 2gh, that's equal to, here we have 392. So therefore, dividing by 2g, you can see here h is equal to 45. So this is the height above O, and therefore we can conclude here that the greatest height, that's equal to the 20, this is 25. No, it's not, it's 20. So we have the 25 plus the 20, which is 45 meters. Now, for part C of the question, in a refinement to the model of the motion of the ball from O to A, the effect of air resistance is included. This refined model is now used to find a new value of u, how would this new value of u compare with 28, the value given in part A? Well, over here, the new value of u is greater than 28. That's if we include air resistance. And now for part D, state one other refinement to the model that would make the model more realistic. So one possible answer is we could use a more accurate answer or value of g instead of the 9.8. Okay, so instead of the 9.8.